All right, so in the world of blockchain, speed is, well, it's pretty much everything. But here's a huge problem. How do you get thousands of computers all over the world to agree on the exact time, right down to the nanosecond, when there's no central clock to look at? It's a massive challenge. Today, we're digging into something called proof of history, a really clever but also pretty controversial piece of tech that claims to have cracked this exact problem. We're going to break down how it works, what makes it so mind-blowingly fast, and also get into why some folks think it might just be a fragile shortcut.
Okay, let's start with a simple question, a little thought experiment. Imagine you and I are in totally different cities. How can we prove, without a shadow of a doubt, who sent a message first? We can't trust a central server, right? No Google clock, nothing. For a global network of computers, this isn't just a fun little puzzle, it is a fundamental roadblock.
So yeah, for a decentralized network like a blockchain, this isn't just a hypothetical. It's a huge, real-world technical hurdle. You see, without a single trusted source of time, all these different computers, or nodes, have to waste a ton of time and resources just chattering back and forth to agree on the simple order of events. This whole mess is what we call the clock problem, and it's a massive bottleneck for performance.
But what if you could just build a clock right into the blockchain itself? Well, back in 2017, an engineer had exactly that light bulb moment.
And that engineer's name was Anatoly Yakovenko. Now, this guy had spent over a decade at Qualcomm, deep in the weeds of complex distributed systems. Then, after stints at Mesosphere and Dropbox, he had this breakthrough. In 2017, he dropped the white paper for what would eventually become Solana. And in it, he proposed a totally new way to create an ordered, verifiable record of events.
He called it proof of history, or POH for short. So what is it? At its heart, it's basically a cryptographic system for creating timestamps. Think of it like a decentralized stopwatch that's built directly into the blockchain, embedding proof that time is actually passed right into the data itself.
Okay, now this next part is absolutely crucial, so listen up. Proof of history is not a consensus mechanism. It doesn't decide if a transaction is good or bad, valid or invalid. That job still belongs to something like proof of stake. No, POH is what we'd call a pre-consensus tool. Its only job, its one and only job, is to put all the transactions in a verifiable order before they even get looked at for validation. And by doing that, it just slashes the amount of back and forth chatter the nodes have to do.
So how does this crypto clock actually tick? Let's pop the hood and get into the core mechanics.
The engine powering this whole thing is a really cool cryptographic concept called a Verifiable Delay Function, or VDF. And honestly, the name kind of says it all. It's a special kind of process that's designed to prove a certain amount of time, a delay, has passed. But here's the magic trick. It is intentionally slow and step-by-step to compute, but it's lightning fast to verify.
So here's how it actually works. It's surprisingly simple, really. Step 1, you start with some random value. Step 2, you hash it using SHA-256 to get a new output. And here's the key. Step 3, you take that output and use it as the input for the very next hash. And you keep doing that over and over and over again, creating this long, unbroken chain. Because each link in the chain depends on the one right before it, there's just no way to cheat or calculate them all at once. You have to do the work one step at a time.
And each one of those hashes, you can think of it as a single tick on this cryptographic clock. So the longer the chain of hashes gets, the more time has passed. It creates this super solid, verifiable record of time. There is just no way to skip ahead to hash number 1 million without first calculating all 999,999 hashes that came before it.
Now this is where it gets really powerful. When a new transaction shows up, its data gets mixed into the chain. It's basically stamped right into the current hash. And because of that, it permanently changes every single hash that comes after it. It's like a ripple effect that you can't undo. This gives the transaction a totally immutable, verifiable timestamp and locks it into a specific point in history.
Okay, this right here is the absolute heart of why proof of history is so efficient. Creating that timeline, it's a grind. It's slow, it has to be done sequentially on a single CPU core. But verifying it, that's a completely different ballgame. Since you have the whole list of hashes, you can throw thousands of GPU cores at it and check different parts of the chain all at the same time.
And this is exactly what we're talking about. The verifiers can take that long chain, chop it up into a bunch of smaller slices, and check all of them in parallel. The result? The entire network can confirm that the history is legit way, way faster than it took that one single computer to create it in the first place. It's a brilliant, asymmetric design.
All right, so that's the how. But so what? Why go through all this cryptographic gymnastics? The answer, in one word, is performance. We're talking about raw, unadulterated speed.
Because you have this reliable global sense of time, nodes don't have to waste time arguing about the order of events anymore. That communication overhead just gets slashed, and the result is a ridiculous leap in throughput. Just look at the difference here. A network like Solana, which uses proof of history, can process thousands of transactions per second. That absolutely dwarfs other networks that are stuck constantly talking to each other just to figure out what happened when.
And when you have that kind of high throughput, another amazing thing happens. The costs just plummet. It's simple, right? When you can process transactions that efficiently, the fees just fall through the floor. We're talking about fractions of a single penny here. It's almost free.
But wait, there's more. The benefits don't stop at speed and cost. With proof of history, transactions get locked in, what we call finality, much, much faster. They become irreversible almost instantly. And it's also a powerful defense against attacks. To fake the history, a bad actor would literally need a computer faster than the entire network's clock, which is basically impossible.
Okay, but it's not all sunshine and roses. Proof of history is really innovative for sure, but it's got its fair share of critics. And they raise some really serious questions about the trade-offs being made here.
So let's start with the practical stuff. First off, to run one of these proof of history generators, you need some seriously powerful, specialized hardware. We're talking expensive. And that high cost to play could lead to centralization, where only a handful of wealthy players can actually afford to participate. On top of that, having just one computer generating the timeline at any given moment, well, that looks a lot like a single point of failure, doesn't it?
And then you have the really deep theoretical critiques. A researcher named Victor Schaut points out something pretty fundamental. He argues that proof of history is actually a very imprecise clock. And why is that? Because its measurement of time isn't based on seconds. It's based on how many computations have happened. This means its speed is completely dependent on the hardware running it. A faster computer literally means time moves faster on the network. This really calls into question whether it can be considered a reliable, universal source of time at all.
So that leaves us with the big question, right? Is proof of history this elegant, brilliant solution that finally unlocks the kind of performance we need for a global scale? Or is it a fragile, computationally expensive shortcut that ends up trading decentralization for pure, raw speed? Honestly, the debate is far from settled, but the answer is going to play a huge role in shaping the future of high-performance blockchains. Thanks for diving into this with us today.